Bismillahirrahmanirrahim. Welcome to this week's class of Digital Communication. I am your course instructor Dr. Naveed Mufti at the Department of Telecommunication Engineering, University of Engineering and Technology, Mardan. So last week we looked at error detection. First of all, we looked at different automatic retransmission query techniques, and then we went on to look at some single and two alphabet examples from English language. It was followed by a code decode example, a paragraph from English language, just to give you an idea of how error decoding works. And then we went on to discuss that there are basically two types of error detection or error correction codes, block and convolutional. Then some terms that we need to be familiar with when we are studying error coding. We went through those terms. And thereafter we started looking at error detection codes, starting off with the very simple single parity system, and then moving on to BCC, and finally CRC. This week, now we will be looking at error correction codes. So first of all, we will get ourselves familiar with the concepts and the terminology related to error correction codes. And then we discuss some basic introduction of Hamming code. After having gained this knowledge, then we move on to see how we basically implement the encoding part, so how we construct a Hamming code. After having understood how Hamming code is constructed, then we will look at some examples of Hamming coding, and then we will look at some examples of Hamming decoding. And finally we will have a few notes on Hamming code, and we will end Hamming code by discussing variants of Hamming code. Once the discussion of Hamming code is over, we will be once again comparing block and convolutional codes and agreeing that there is a common target for error control for any type of error detection or correction codes. So the learning outcomes for this lecture are that the student should be able to interpret basic terms related to error correction, determine Hamming distances and weights, determine if given codes are linear or systematic, explain and illustrate the construction of 7/4 Hamming codes, decode received sequences, infer the working of different variants of Hamming code, and finally compare block and convolutional codes. Okay, so on the previous slide we discussed that CRC is basically an error detection technique, but with some good planning it can also detect the location of the error. That means it is also able to correct an error, and we discussed one example how it can correct an error as well. So now coming over to some more terminologies which are needed for our further discussion of channel coding. Since we are moving forward to now error correction codes, there are some few terms that you need to be familiar with. So the first term is the term code. What does it mean? So basically in digital communication or in information and coding theory, the term code refers to a collection of code words. So whenever from this moment onwards, when we refer to a code, basically we are talking about a collection of code words. Okay, so that's the first definition you need to be clear about. Then the second thing is related to what is a linear code. Okay, what is a linear code? So a linear code is when we add the extra parity bits, and those extra parity bits basically they are found by linear combination of data bits. So the values of parity bits are determined by a linear combination of the data bits. That is the first thing, that is the first property of a linear code. And then what you have to remember further in addition to that is that the all zeros combination will be present in a linear code. So one of the code words in a linear code will be the one which has all the bits as zeros. So all zeros combination is present. That's the second thing you need to remember. And the third thing is that within that linear code you will have different code words. So if you do XOR operation of any two code words, so that means a modulo 2 sum of any two combinations, it it gives you the result which is already present in that code. So the result is also one of the code words present in that code. So if a code is linear, it will be satisfying these conditions. So basically these terminologies are related to block codes. Okay, so now since we are talking about error correction, so the first thing we will be discussing are block codes. So in the block codes, the number of message bits is fixed, it's k, and the number of total coding bits is also fixed, that is small n. So the number of parity bits we add are n minus k, as we discussed previously. So all those things they apply here. So basically we are talking about an nk code word, nk notation for a code, and n is the total number of bits including message bits and parity bits, and k is the number of message bits, so that means the number of parity bits is n minus k. So a linear code, I have explained to you what properties need to be there in order to be termed as a linear code. And then a systematic code is a special case of linear code. So in a systematic code, what will happen is that a special case when in the code word, the first bit is the same as the first bit of data word, the second bit is the same as the second bit of data word, the third bit is the same as the third bit of data word, and the fourth bit is the same as the fourth bit of data word. So for example, if the number of data bits are 4 and they are in a particular order, and the code word that you generate for that data word, that code word, the first 4 bits of that code word will be the same as that the data word, and then the parity bits will be added. The parity bits, they will obviously be additional bits, and they will be the linear combinations of these message bits. So if a code satisfies this property, that is called a systematic code. So what I am trying to say in other words is that in a systematic code, the first k bits of the code word are the data bits, and the last n minus k bits are basically the parity bits, which are formed by the linear combination of the data bits. So a systematic code is basically a subset of a linear code. So if a code is systematic, it is automatically linear. So that's what you need to remember. I'll give you an example on the next slide, and it will become clear. And then the next terminology is Hamming distance. So the Hamming distance is basically the number of elements or bits in which the code words differ from each other. So we calculate the distance between two things. So the Hamming distance is calculated between two code words, and that is basically the number of bits or bits positions in which the two code words are different. So that's easy to calculate, that's not so difficult. And then another term is Hamming weight. And Hamming weight is simply the number of non-zero elements in a code, or the number of ones in a code word. So in a code word, if you count the number of ones, that is the Hamming weight of that code word. Now interestingly, Hamming distance and Hamming weight have an interesting relationship, and that is that the Hamming distance between any two code words is equal to the Hamming weight of their sum. That means XOR. And also the Hamming weight of a code word is equal to its distance from the all zeros vector. So you can verify these statements by taking any examples of code words. Okay, I'll move on to the next thing, which is the error detecting capability. So if there are many code words within a code, there are a set of different distances between all pairs of code words. So you can have many different Hamming distances between the code words of a single code. Now once you have all those distances between all the different code words, there will be a minimum value. So that smallest distance, that is called dmin. Okay, and that value is important because the error detecting or the error correcting capabilities of codes, they depend on the value of dmin. So that dmin, just let me quickly mention it. Okay, so the error detecting capability, first of all, that is indicated by E, and that is dependent on dmin. In fact, that is equal to dmin minus 1. That is equal to dmin minus 1. That is the error detecting capability of a code. And then the next is error correcting capability. The error correcting capability is denoted by T, and that is equal to dmin minus 1 by 2. So basically you can say E by 2. Okay, so basically error detecting capability is less than the error correcting capability is less than the error detecting capability, because that is a more complex procedure, and error correcting capability by default involves error detection as well. Okay, so when we say that an error is corrected, obviously it will be detected before it can be corrected. So that's what you need to remember as well. So both these error detecting and error correcting capabilities, they depend on the value of dmin. So the target, while we are creating code words, usually one of the targets is to have the value of dmin as large as possible. And the bigger the value of dmin is, the more enhanced is the error detecting and error correcting capability of a code. So that is what you have to remember. Now there is a compromise or a limit to how we can balance error detecting or error correcting capabilities. So a code can be used for simultaneous correction of alpha errors and detection of beta errors. So we can perform them simultaneously. So we can correct alpha errors, we can detect beta errors where beta will be greater than or equal to alpha. But they both have to satisfy an equality. Okay, and the inequality, I'll just mention it here. Dmin should be greater than or equal to alpha plus beta plus 1. So once again, what is alpha? So this relates to simultaneous correction or detection. Okay, so alpha is related to correction, so alpha is related to T, beta is related to detection, so beta is related to E. So this is the inequality that they have to satisfy, and it is possible to trade off correction with simultaneous detection. So we can do a trade off. For example, if dmin is 7 and we want to perform simultaneous detection and correction, so we have a choice then. We can either have the value of beta as 3 and alpha as 3, or we can have beta as 4 and alpha as 2, or beta as 5 and alpha as 1, or beta as 6 and alpha as 0. So we can take all of these combinations. So basically, but we have to remember that beta will always be greater than or equal to alpha. So alpha cannot be greater than beta. That's what you need to remember. So that is how they are interrelated. Okay, so here I've given you an example of a code. This code has 8 code words, as you can see on the screen. Now I leave it to you as part of a verification and extending your understanding to verify whether you can call this code linear. So that's the first thing you need to check, whether this is a linear code or not, and then secondly you also need to check whether it is systematic or not. So do a self-assessment of this code given on this screen and reach a conclusion whether the given code is linear or not. So now we move on to discussing the first type of block code, which is called Hamming code or Hamming coding. So Hamming coding is a type of linear block code, and we will be discussing the construction of Hamming code. We've already discussed the relationship between alpha, beta and gamma. We will also briefly discuss extended Hamming code. We have done Hamming distance, Hamming weight, and we have done systematic code. So some of the terminologies we are familiar with and some things we'll be looking at. So here on this slide I will discuss the construction of Hamming code, and for the construction the easiest way to do is to use a construction table as I've shown on the screen. And because Hamming is a block code, so the length of the data word and the length of the code word, they need to be fixed and pre-decided. So here in this example we are using the NK code with the value of n as 7 and with the value of k as 4. So basically we are taking 4 data bits, and for this example I've chosen the data bits combination to be 1011. So first of all you need to draw a table like that, where the first row can be the bit positions. Because it's a 7/4 code, so you need 7 bits, so 7 bit positions here. And then the second row is basically the binary equivalent of the bit position. So because there are 7 positions, we need 3 bits to express the binary equivalent of every position. So here we have the binary equivalents of all the bit positions as shown here. And then the third row is that of the bit status. So in this the bit positions are fixed, which bit positions will be of parity bits, which bit positions will be of data bits, that is fixed or pre-decided. So in this regard, please note that all the bit positions that are powers of 2, that are parity bits, that is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2 and so on, they are the parity bits positions. So 2 raised to power 0 is 1, so the first bit position is parity bit. 2 raised to power 1 is 2, so that is also parity bit. 2 raised to power 2 is 4, so that is also parity bit. And then the rest of them are data bits in the same order. Okay, and these are the numbering, so that you are clear that this parity bit is of position 1, position 2, this data bit is of position 3, this parity bit is of position 4 and so on. And then finally in the last row you can have the value of the bits. So right now at this moment you just have the value of the data bits 1011, 1011. You don't know yet the values of the parity bits. So you just put a cross here, and once you know the values of parity bits, then you can obviously replace these crosses with those values. So that's your Hamming and coding process. So before we proceed further, I would like to tell you that so the bit positions that are powers of 2 are parity bits, and the other bit positions, they are the positions of data bits. Now parity bit 1, that basically the equation or the value calculation of parity bit 1, that will involve all the bit positions, that will involve all the bit positions whose least significant bit in binary representation is 1. So if you look at the bit positions, if you look at these bit positions, this is the least significant bit, this is the least significant bit. So all those bit positions whose least significant bit is 1, they are the ones who contribute in making or deciding the value of parity bit P1. So in this case here, parity bit 1 P1 itself, this D3, D5 and D7. So these bits will all contribute to decide the value of parity bit 1. Now coming over to parity bit 2, parity bit 2 basically covers all the bit positions whose second last bit in binary representation is 1. So going back to the our binary representation, second last bit is 1, not this one. So the parity bits itself, D3, not P4, not D5, then D6 and D7. So for parity bit P2, its value will be decided by these bits P2, D3, D6 and D7. And now the third parity bit P4, the rule for that is that it covers all the bit positions whose third last bit in binary representation is 1. Third last bit. So that was the least significant bit, that is the second least significant bit, this is the third least significant bit. So all those bit positions whose third least significant bit is 1, they will decide the value of parity bit 4. So that means P4, D5, D6 and D7, they will decide the value of parity bit P4. So that is how the parity bits are linked to unique positions, or their values are determined by linear combinations of data bits, as you will see on the next slide as well. So Hamming coding, as I said, that's a type of linear block code. So quickly you may recall what is linear, what satisfies the conditions for linearity. So that is a linear code, and it can be a systematic code. Okay, so Hamming code can be a systematic one. So it can be a systematic code. And now we discuss the construction of Hamming code, and we'll start by looking at example of a 7/4 Hamming code. So this represents n, and that is k. So that means that we will take a block of 4 message or data bits. It's a form of block coding. So in block coding we have fixed block size of message bits and a fixed block size of code word. So there is a fixed block size of data word and there is a fixed block size of code word. So here in 7/4 we take 4 data bits, a block of 4 data bits, and we add 3 parity bits to make a total of 7 bits. So our final code word will be of 7 bits. So let us say, for example, this is our message 1011. These are our data bits, and we are using odd parity to come up with the values for parity bits. Now the parity bit 1, the parity bit 1, this is the equation for parity bit 1. Parity bit 1 has got its own unique equation, and that is how the parity bit 1 is calculated. This is the equation for parity bit 2, and that is the equation for parity bit 3. So based on, as you can see, all the values of parity bits, they are determined by a linear combination of the values of the data bits here. So we can calculate the values of parity bits. If we are using odd parity, the result of this equation should be 1. If we are using even parity, the result of this equation should be 0. So after solving these equations, we are able to generate a code word with odd parity, which is this. So the order of the bits is that these are parity bits and these are the data bits, the message bits that were here. So do you get the same answer if you want to calculate the values of parity bits like that? Check what are the values of parity bits you get when you try to calculate the values like this. So now we come to the decoding. So basically, to check for errors, all the parity bits, they are checked, so their equations are checked. If all the equations are correct, there is no error. If they are not correct, there is an error. So how does the receiver identify? Basically, there are a few things you need to remember. So the receiver knows the parity, whether odd or even parity was used. So the receiver also knows the positions of the parity bits because it is pre-decided. And the receiver receives the noisy code word. So based on the noisy code words, so based on the bits that it receives, based on the values of the data bits it receives, it can assign the values to the parity bits. So it can itself calculate the value of parity bits using the values of data bits received, and then it can compare those values of parity bits it generated to the values of the parity bits it received. So if they are the same, then there is no error. If they are different, then there is an error. or it can just do the equation verification on the received sequence to see if they satisfy the equation or not. So for example, we discuss now the decoding at the receiver. Let us say that this is what we received. Okay, so this is what the receiver has received, and it knows that there is odd parity. It knows that this is the equation for parity bit P1. So now if we perform a check on this equation and to see if this equation is satisfied by the sequence that is received. So P1, the value of P1 is 1, 1 plus D3, D3 is 0, so 1 plus 0 is 1, and this 1 is then added to D5. So the value of D5 is 0, so 1 plus 0 is 1, and then this 1 is now added to D7, the value of D7 is 1, so 1 plus 1 is 0. So the answer as per this equation, based on the values received, the answer comes out to be 0, whereas the answer should be 1 because odd parity has been used. So this equation is not being satisfied. That means there is something wrong. So it makes a note that okay, there is an error in parity bit 1 equation. Now let's go to the second equation of parity bit 2. So P2 plus D3, P2 plus D3, the answer is 0. D6 plus D7, D6 plus D7, the answer is 0. So 0 plus 0, the answer based on the received sequence should be 0. The answer is 0, but the answer of this equation should be 1 as per odd parity. So it is not satisfied. There is an issue. The left hand side is not equal to the right hand side. So this equation is also not satisfied. That means there is a problem in this equation as well. And now coming over to the last equation, P3 plus D5. So this is P3, 0 plus D5, 0. Sorry, P3, we should call it P4 plus D5 rather. So P4 plus D5. So the answer is 1. Okay, so answer of this sum is 1. And what about this thing, 6 and 7? If we add them, the answer is 0. So basically it's 1 plus 0, the answer is 1. So this equation is satisfied. The left hand side is equal to the right hand side. So there is no problem. This equation is satisfied. So now what do we do then? So the receiver has done these calculations and it has discovered that the equations P1 and P2, they show an error. Okay, so now it needs to locate the error. So that's simple. That means bit 3 is in error. So whichever equations they give you an error, if you add their subscripts, so the equation of P1 and the equation of P2, they had an error. So if you add 1 and 2, that becomes 3. That means bit 3 is in error. So you correct it. You correct the value of bit 3. So this bit 3 here has been corrected to 1, and that is now the corrected sequence. So at the end it's very simple. For example, if only one equation had an error, yes, if only P1's equation had an error, that means the value of P1 itself was an error. If only the value of equation of P2 was an error, that means that the parity bit P2's value had an error. If both equations were in error, just like this case here, that means bit 3 is in error. If the equation of P4, this equation here, if that was in error, that means the parity bit P4 was in error. If these two equations were in error, that means bit number 5 was in error. If this equation and this equation, they were in error, that means bit number 5 was in error. If these two were in error, that means bit number 6 was in error. If all of them had errors, that means bit number 7 is in error. So depending on which parity bits equations are in error, basically bits from 1 to 7, all of them can be identified as to which bit position is in error, and then we are able to correct that bit, and that is where the error correction happens. So let us consider another example. Let us say that this is what we receive. Okay, so we perform a similar check. Our P1's equation shows an error only, so that means bit 1 is in error, so it changes it, but this was incorrect diagnosis. The receiver it wrongly identified the bit in error because there were two errors in the code word. So receiver thinks that bit 1 is in error and then it corrects it, and this received sequence basically changes to this, whereas the actual that was transmitted was this. So you can see when you compare them that now even the received sequence is even further away from the transmitted sequence. So in fact we have added an error in it. So that is also happens when the number of errors increase and go beyond its capability. And as I mentioned earlier, the error detecting or the error correcting capabilities, they depend on d min. So here it was unable to do the correct diagnosis due to two errors in the code word, and it ended up with an incorrectly corrected sequence. So just some final notes on Hamming. Sometimes a 7/4 Hamming code, they cannot tell if 1 or 2 bit errors have occurred in a single code word, and when that happens, that leads to problems as we saw on the previous slide. So with 2-bit errors, Hamming can end up with correcting the wrong single bit error positions, as you noticed in the previous slide. So in such cases, we need one extra bit to address these shortcomings. So that is where we can use extended Hamming code, which is 8/4 code. So we add one extra parity bit. So the status 8 bit is that it is a parity bit. So the bit positions in binary, now they will be, the number of bits for every bit position will be 4 now, and the min in the previous case was 3, now it increases to 4. So the values of E, T, alpha and beta you can calculate, so it becomes enhanced. And the equations, well, these can be the equations for the parity bits. As you can see, the 8th parity bit equation involves all the previous bits, all the 7 bits. So this is a note on extended Hamming code. Now there is also a variant of Hamming where a different bit arrangement exists. So we can have a bit arrangement like this. So all the data bits together and all the parity bits together. We can call them 1, 2, 3, or we can call them 5, 6, 7. Both conventions are used. And the values of parity bits are then calculated using these equations. And we have an example here. So that's your data word and that's your code word generated using these 3 equations. You can verify. And why we have changed the order? Previously we discussed that the bits of the positions of 2 are the parity bits and all the others are data bits. Why we have changed the order? We have made it systematic now. So if you see now, it satisfies the properties of a systematic code. So it becomes a systematic Hamming code. So this is a variant of Hamming which is a systematic code. Okay, so first of all, coming over to the comparison between convolutional and channel encoding. Comparison of block and convolutional encoding. So in block encoding, we have to specify a block size. So we have to wait for a certain number of data bits, let's say k data bits, and for each sequence of k data bits there is a distinct code word of n bits. So the k data bits are first accumulated and then encoded into a n digit code word. So obviously you can expect that there is a bit of delay involved, because unless we have k data bits, we cannot come up with an n bit code word. On the other hand, in convolutional coding, our coded sequence of n bits, it depends on k data bits and previous n-1 data bits also, because it has memory or registers involved. So they store the previous values, but the coding is done on a continuous basis without accumulating. So even if 1 bit is entering the encoder, we can have the output, so we don't have to wait. So there is no encoding delay, you can say there is no encoding delay involved. But obviously, since it is storing previous values, so memory or storage registers, they are involved. And what are the main targets of error control? We want a minimum amount of redundancy. So we know that in channel coding we add extra number of bits. So we want to add a minimum number of extra bits in our system. And we want maximum Hamming distance. So we want our code words to be as far apart from each other as possible. That's the second thing we want. So these are our two main targets in error control. Okay, so that brings us to the end of this lecture. Thank you.